Simple flat file spreadsheets are the standard for tracking data, but at a massive high volume, these simple grids become liabilities that break down under their own weight. Imagine a university attempting to track every undergraduate and postgraduate record within a single unified Excel sheet. This record shows exactly how much information is being forced into a single row: the student's name, number, and NIC, alongside the module code, name and grade, and the degree program details. Forcing distinct real-world entities, students, modules, and degrees, into one flat row creates a structural time bomb. This causes an update anomaly. Changing a module name requires manually replacing text on every student's row. A single typo corrupts the database. The system now behaves as if two different modules exist, even though only the name changed. There is also the insert anomaly. If the university launches a new degree program before any students have enrolled, there is no way to enter that program into the system without creating massive blank voids in the spreadsheet. Flat file systems cannot handle evolving information without generating these errors. Fixing this requires a change in how the data is structured. Addressing these failures relies on Database Normalization, a multi-stage logical framework designed to organize raw data. The first stage is first normal form, or 1NF. This rule dictates that there can be no repeating groups. Every cell must contain exactly one piece of data, or an atomic value. To meet this standard, clumped data strings must be untangled. Every student module combination is moved into its own dedicated uniform row. 1NF makes the data readable by a machine, but it creates massive amounts of repetition, leading to the next stage of extraction. To uniquely identify any row in this grid, we need a primary key. In this example, that requires a combination of the student number and the module code. Second normal form, or 2NF, asks a simple question. Does every other piece of information in this row depend on that specific combination? The logic quickly snaps. A student's name depends on their student number, but has nothing to do with the module code. We resolve this by fracturing the flat grid into 3 distinct tables: one for students, one for modules, and a bridging table for grades. Isolating these real-world concepts into their own tables is the main defense against unnecessary data duplication. Within the newly created student table, we apply one final filter: third normal form. But there is still a lingering issue. The degree program name is determined by the degree program code, not by the individual student. This is a transitive dependency. These columns must detach from the student table to form a fourth independent table for degree programs. The raw data has now passed through the normalization pipeline, resulting in a structure where every attribute is strictly linked to its primary entity. The final result is an interconnected web of students, modules, degrees, and enrollment records. If the university needs to change a module now, they edit exactly one single cell in the module table. That single update is instantly reflected across the entire system, without the need to modify thousands of student records. This logic prevents the insertion and update errors that made the original spreadsheet so difficult to manage. Normalization aligns data with the real-world entities it represents. It is the logical blueprint ensuring information remains accurate and accessible as systems grow.